Next, we want to discuss moving or flowing fluids. Fluid flow can be laminar, and laminar is another word for streamline flow. Streamline flow is very smooth, and each particle passing a certain point will travel along the same path. So in this first picture here, you can see some nice, smooth, laminar flow. Turbulent flow, on the other hand, is very irregular, and it has in it eddy currents, which are like little whirlpools inside the flow where the fluid flow direction turns around or swirls or churns. So this picture here shows some very turbulent flow. Contributing to this is viscosity, which we'll look at a little bit more later on. Viscosity is the amount of internal friction. Water has a very low viscosity. A fluid like molasses has a very high viscosity and flows slowly because there's a lot of internal friction inside the molasses. So for some of the expressions we're going to be looking at next, these expressions are based upon the idea of an ideal fluid. An ideal fluid is a model kind of like the ideal gas model, which works pretty well and is a good description of fluid flow as long as the fluid is very nearly non-viscous. So the ideal fluid model works pretty well for water, and it doesn't work so well for a viscous fluid like molasses. The ideal fluid model also assumes that the fluid is incompressible, meaning it has a constant density. You can't squish it down to make it fit in a smaller volume. Once again, this is a very good model for water, and most other fluids too are fairly incompressible. The ideal fluid model assumes that there is steady motion and no turbulence in the flow, so it assumes a nice, smooth, laminar flow. If those conditions are met, you can calculate the flow rate through some area. So let's assume that we have a pipe and there is fluid flowing through that pipe. And the pipe has a cross-sectional area A, and the fluid is flowing with a speed equal to V. If we look at the volume of fluid that passes through some slice of the pipe in some amount of time, then that volume is going to be equal to the distance that the fluid travels in the pipe. So in some amount of time delta t, all of this fluid has passed through the surface A. So we can multiply that distance of fluid times the cross-sectional area to get the volume of this cylinder of fluid that has passed through the surface A in this delta t amount of time. So that gives us the volume of fluid that passes through the surface in that time. Then the flow rate, which we represent with Q, the flow rate is the amount of volume flowing per time. Well, we just take this volume expression and divide by delta t, which gives us V times A. So that means that if you multiply the cross-sectional area of a pipe times the velocity of the fluid, that will tell you how much volume passes any point per unit time. Another important concept with fluid flow is continuity. So continuity has to do with the fact that if you have some pipe, and it doesn't matter the shape, if you stuff a certain amount of fluid in one end, the same amount of fluid is going to pop out the other end, because the pipe can only hold so much fluid. And so we can express this as the amount of mass, fluid mass, that you stuff in one end is going to be equal to the amount of mass that comes out the other end. And mass, we know, can be expressed as density times volume. And in this case, the density of the fluid that you're putting in one end times the volume of fluid that you're putting in that end will equal the mass. And the volume is going to be equal to that cross-sectional area times the distance that the fluid moves in the one end of the pipe. And that's going to be equal to the same expression on the other side, as this will tell us how much fluid comes out the other end. So that's the density of the fluid times the volume that squirts out the other end of the pipe. So next, what we can do is we can say that, well, the distance that the fluid travels into the pipe is equal to the speed with which the fluid is flowing into the pipe times the amount of time. So distance is equal to velocity times time, assuming a constant rate of flow. And the same expression holds for the distance at this end of the pipe that is losing fluid as the fluid squirts out. That's also equal to velocity times time. Well, we can divide both sides of this equation by delta t, since it appears on both sides, and get this expression here. And then we can, if we assume that we have an incompressible fluid, which is typically true for most fluids, the density of the fluid is going to remain the same, and so densities will cancel, and we get this expression here. So what this is saying is that if we have a pipe and the ends are two different sizes, that if the end of the pipe, or if the cross-sectional area of the pipe gets smaller, then the velocity will increase to make sure that this quantity remains constant. So when the area gets small, the velocity gets bigger. And so you can see this in a couple of different places. So if you go into any sink in your house and you turn it on, you can watch the stream of water coming out of the sink. And as the water falls from the sink, it's going to be in free fall, so it's going to speed up. And as it speeds up, the cross-sectional area of the stream decreases. So here it's wider than it is down here. So you can amaze your friends and family by showing them that this is the continuity equation in action. And as the velocity of the fluid increases, the cross-sectional area decreases. Here's another example where we can see continuity in action. So I'll ask you the question, if you have a younger sibling or cousin or nephew or niece or something and you want to squirt them with the hose, but you don't have one of these gizmos, what do? Well, you stick your thumb over the end of the hose. And by sticking your thumb over the end of the hose, you're making A smaller. The area that the fluid has to pass through is smaller, and so it speeds up. And since it speeds up, the hose does a much better job of squirting. And that's what is happening here with this aerator, or this attachment to the hose. It's forcing the water through some very small openings, so the area that the water is flowing through decreases, so the velocity of the water increases. Another important equation that has to do with fluid flow is Bernoulli's equation. And Bernoulli's equation is a direct consequence of energy conservation. In fact, if you look at Bernoulli's equation, it does look an awful lot like conservation of energy. I mean, here's a kinetic term, here's a gravitational potential term, and the same on the other side. And so what Bernoulli's equation says is basically the kinetic energy and plus the potential energy of the fluid is conserved, but you also have to take into account the pressure difference. So pressure can also add energy to a fluid. And so this quantity here is conserved. And if we look at the density of the water and the pressure at one end and how fast the water is flowing and any changes in height, we can predict how fast the water will be leaving the other end of this pipe that the water is flowing through. So we can take Bernoulli's equation and use it to analyze a specific device called the Venturi tube. So with the Venturi tube, both ends are at the same height. Since both ends are at the same height, we can set that equal to the y equals 0 level. And so the potential energy terms, the gravitational potential energy terms, drop out of both sides of this equation since y is equal to 0. And so then that simplifies the Bernoulli's equation to this expression. The thing that's special about the Venturi tube is that the cross-sectional area of the pipe changes, and A2 is less than A1. Since that is true, since we know that is true, then since A2 is less than A1, we know that whenever a tube constricts and the cross-sectional area gets smaller, that the fluid will speed up. So V2 is going to be bigger than V1. So as the fluid flows through, the area gets smaller, the velocity of the fluid gets faster. So if the velocity of the fluid is getting faster, then that means the pressure decreases. And so we can take from the Venturi tube the lesson that if the flow gets fast, the pressure of a fluid gets lower. So fast flow is equal to low pressure. So next, let's take a look at this example problem. We have water, which has a density of 1,000 kilograms per cubic meter, flowing at 15 meters per second through a pipe with a radius of 0.04 meters. The pipe goes up to the second floor of a building, 3 meters higher, and the pressure remains the same. So what is the speed of the water flow in the pipe on the second floor? This sounds an awful lot to me like a Bernoulli equation problem because we're talking about a difference in height, and we're also worried about the speed of the fluid in this pipe. So we can probably tackle it using Bernoulli's equation. First, though, let's draw a picture of the situation so that we can figure out what quantities are appropriate to use where. So in this situation, we have a pipe, and the pipe goes up to a higher height as it goes up to the second floor of a building. And we know that the difference in height is 3 meters. So I'm going to call the lower height, this ground level height, I'm going to call this the y=0 level. And up here, we'll say that this is, and we'll call this y1. So we'll say everything having to do with this end of the pipe is 1, everything having to do with this end of the pipe is 2. So y2 is going to be 3 meters. So we're also told that we have water with a certain density. We're given the radius, and we also know that the 15 meters per second is the velocity of the water as it flows into this end of the pipe. So V1 is going to be equal to 15 meters per second. And we also know the radius of the pipe is equal to 0.04 meters. And the radius of the pipe doesn't change. We're not told that the radius is different on one end than the other. So this is going to be equal to R1. It's also going to be equal to R2. So the radius of the pipe does not change. Then we also have the pressure. So on this end, we have P1, and at this end, we would have P2. But once again, we're told that the pressure doesn't change. So I'm going to say P1 is equal to P2, and I can use the same symbol for both since they both are the same amount. So next, now that we have an idea of what this situation is like, and we know we want to find the volume or the velocity up here, V2, of the water exiting the pipe, now that we have all of that sorted, we can write down Bernoulli's equation. So Bernoulli's equation says that P1 plus 1/2 rho V1 squared plus rho, since we're dealing with this fluid, rho G Y1 is equal to P2 plus 1/2 rho V2 squared plus rho G Y2. All right, so as is the case when we are conserving energy, we should look to see if any of these things are going to be equal to 0 and if we can simplify this expression further. Well, we know that y1, as we've defined our coordinate system, y1 is 0. So that means the initial thing that's like the potential energy term, that's going to be equal to 0. So that makes things simpler. And we also know that both P1 and P2, pressure 1 and pressure 2, are equal to the same pressure. So I can actually just scribble out the subscripts here, because both of these are equal to P. So then what I can do next is subtract p from both sides of this equation. Minus p, and I'll subtract over here minus p as well. So if I do that, I have a p minus p, so that gets rid of the pressure over here, and a p minus p, which gets rid of the pressure over here. So then I have a simplified equation, 1/2 rho v1 squared is equal to 1/2 rho v2 squared plus rho gy2. All right, so if I want to simplify things even more, I recognize that I have a density in each term of my equation, so I can divide all of the terms by rho, and so that cancels those out. And since I want to also solve for V2, I want to know the velocity of the water up here at the higher level, then if I want to solve for that velocity, I can also simplify things by multiplying all of the terms in the equation by 2. And the 2 will cancel with the 1/2 here, and then I get 2 gy2. So now I'm left with v1 squared is equal to v2 squared plus 2gy2. So now I just have to subtract this term from both sides. So v2 squared is v1 squared minus 2gy2, and then take the square root of both sides. So that leaves me with a v2 is equal to the square root of v1, which was 15 meters per second, square that, minus 2 times 9.8 meters per second squared, times y2, which was 3 meters. And so that gives me a velocity, which is equal to about 12.9 meters per second. So that's going to be the speed of the water when it's in the pipe up here at the 3-meter level on the second floor. Next, let's talk about lift. So we saw before with the Venturi tube that fast fluid flow means low pressure. And with lift, you have air that's moving around a wing. And since, as you can see, due to the shape of the wing and due to what's called the angle of attack, the fact that this wing is kind of lifted upward, the air that flows over the wing is compressed into a smaller area. A small area means fast fluid flow, and so the air moving over the wing moves faster than the air moving under the wing. And you can kind of see that happen in this animation over here. So since the air moves faster over the wing than under the wing, then we have lower pressure above the wing than below the wing, and since there is lower pressure, there will be an overall force upward.